Hey, let me remove the getting started soon because we already started. Um, hey, how are you? Good night, good morning. I don't know what time is it for you. For me, it's good night. It's 10 p.m. But I've been doing streams all day, so probably of you. Uh, Probably many of you were watching my first streams in the night, and now you wake up and watch me again. I hope. So let's start reading some comments here. Sri Shev says hello. Oh, Sal says hi. Uh, uh, like a hugging little yellow ball. Hey, did you guys build the database career optimizer? Has anyone tried? Oh, you're talking about the challenges. I think that's the hardest project to build in this data week. Yeah, that could be very challenging. I agree on that. But it's a good thing that you're trying to reach to other hackers to see like how they are doing. Great, kudos on that. So Strandev says good morning. So it's good morning for you. Cool. So remember to put you in a little bit of context. This is the part three of the neural network using MATLAB. In the part one, we checked a lot of the theoretical aspects, like a little bit of history. We said the difference between, for example, neural networks and artificial intelligence, that you can do artificial intelligence without neural networks, and also you can do neural networks without artificial intelligence, like what we did in part two, for example. But also they are really correlated um, in many, many ways. Like, for example, with deep neural networks and deep learning, like you have to do deep neural networks when you're doing deep learning, right? But just a little bit of those theoretical aspects. Things to have in mind. Remember what a neuron is. We check the biological inspiration. We have axons, we have the cell body, and we have like the dendrites. We have the synapses where these where the axons of one cell body connects to the dendrites to another one. So it's the connection, but that's for the biological one. Sorry. Well, then we check the model of a mathematical neuron, the definition of the architecture of neural network, how we can have just one input, one neuron, and the output. That's a neural network, but we can also have many inputs, one neuron, many inputs, many neurons. Then we have a layer that we can have multiple layers, and well, then we can start experimenting with many things. Then we introduced concepts like the bias, that's not part of the biological inspiration, the transfer functions, that it's what we want to mathematically apply to the sum of the weights times the inputs plus the bias. We apply the transfer function to that. And again, I'm just doing a little recap. You have more questions about what I'm talking right now. You can check the part one, it's recorded. Then we start taking a look to the Hamming network, which is a specific type of network about the recurring networks, RNN, recurrent neural networks. And we also talked, thanks to a great questions about a hacker, about these neural network zoo, which is a document that contains many of the architectures available. And well, we've been talking about, for example, also other great resources like the book, The Neural Network Design by Martin Hagen, which is the one that which is the one inspiring all these series of sessions. I shared a repo that, with the code which I am presenting for these sessions, a repo of the original code I inspired to get my code, which is writing in Python. Mine is writing in MATLAB. And some other repos about how people complete exercises in this book, right? What else? I think that's it. Well, another important thing to mention, and that you probably missed if you didn't watch the previous part, it's that designing artificial neural networks, it's like cooking. You have recipes about network architectures. You can build, for example, the part two, we build the Hamming neural network. So you have the recipe, what ingredients you have to add, like neurons, like the weights, matrices, like how to design the bias, and blah blah blah. And at some point, you will be skilled enough to create your own recipes. So that's the main idea here, right? Uh, Now, previous in the previous session, we completed the Hamming neural network. We checked that. We see how we can classify through an binary vectors, like yeah, it's a requirement for that. We have to set binary inputs to classify in based on prototype vectors, and we get the output on a vector that it's resulting. The resulting class will be the non zero value of that vector. But as I was mentioning, we didn't introduce any learning rule. We made the neural network just ourselves. So we created the bias, we created the weight matrix, and we did that, and we designed that to perform the classification, right? So we tested, we even checked some exercises, and it was good. Now we're going to introduce a new artificial neural network that is the perceptron. The perceptron, it's very similar to what the what the first neuron, artificial neuron, was in the world, like the one introduced by Macaulay Pitts, and the one that started this wonderful world about neural networks, right? Well, artificial neural networks. But the main difference with that, the first in what that was introduced, and the perceptron, it's not in the complexity, because both are very similar, um, but in the learning rules that was applied and that was introduced uh, in this paper. You can check the paper. I will give you the name. But the important thing here, again, it's more than the architecture itself, because we can do it manually. We can set and construct the bias and the weights and everything in order to do the classifications manually. Um, the more important thing here is the introduction of the learning group. So it's what it started correlating at first place neural networks and artificial intelligence, and I think that's one of the highest valuables on neural networks, like the ability of the algorithms to adjust themselves to perform tasks, to learn, you know, to learn how to perform these tasks. So, enough of me just talking directly to you. Let's open the book and start reading this interesting perceptron. Let me start sharing my screen. Screen one. Okay, now you should see it here. Amazing. So these were some of the examples we were checking on the chapter we were taking a look. Let me return. No, let me advance to the next one. A checking link you forgot today too. Oh, thanks a lot. You saved me. Thanks. Yeah. I always forgot to send this link. Yeah. So yeah, remember to check in to get your points for this session. Thanks a lot. Okay, yeah. Continuing, blah blah blah. The illustrative example. This is the fruit classifier we built for the Hamming network. But if you look, the perception it's even before the Hamming network. Why I started with the Hamming network then? Because I think now there are some considerations on the perception that you will need to understand before getting to this. But now we completed the Hamming. You can take a look also to the Hope field. It's very interesting, but more complicated. And designing it, it's not even shown in this chapter. There is a dedicated chapter for that. That's why I'm skipping the Hope field network. I started with the Hamming one, and I wanted to follow up with the perceptron. Let's take a look to the perceptron. In our example, let's recall we had a fruit classifier. We said that we had a sensor that can detect shape, texture, and weight. If the shape it's rounded like, it will give us a one. For example, a prototype orange and a prototype apple. Those ones will be ones. If the texture it's like rough, it will give us a -1, else it will give us a 1. So for the orange it will be -1, and for the apple that will be 1. And the weight, we set a limit. Both are liked fruits, so both have -1 because it doesn't passes the threshold value for this. So these will be the prototypes of the orange and the apple, right? Remember that, and we will be good. The neural network will receive this three dimension, blah blah blah. Okay, don't worry about this. The perceptron. In this first network, we will discuss the perceptron. Uh, this figure illustrates a single layer perceptron with symmetric hard limit transfer function. A thing to have in mind is that perceptron can have hard limit, and normally you will see it with hard limit. But in this time, they taking a license to do this symmetrical. Remember the transfer function; it's the ones that decide with what the output should be. And for the hard limit, every value that is more than zero or greater than zero, all values will be set to one. If a value is lower than zero, less than zero, it will be set to zero. So it turns the output in a binary decision. And this is important because we are going to classify, right? So you can take an idea of why this binary output is important. Because I remember someone, I think it was OIP, asked if how we decided the transfer function we want to use. Again, in general terms, recipes already have a transfer function. I mean, we cannot be doing a perceptron and putting here logsim, or purely transfer function, right? It's the perception. Perception. It's built with hard, and in this case with hard limbs. Um, but in the future, if you want to do something similar or things like this, or make even a more complicated one, because perception it's very easy. It's very simple, very elegant, and very powerful. But it's easy in matters of trying to understand this. Uh, like by hand, because even for the Hamming one, we have two layers, the feed-forward layer and the recurrent layer. In this one, we only have one layer. And perceptron, it's only one layer. In this case, we're talking about a perceptron of one neuron. This is a single layer perception with a symmetric Hall limit transfer function. Again, this is the general sketch of the perceptron. Remember, we have a vector input of r dimension, r times 1. We have our weight matrix that will be depending of s, the number of neurons, r, the number of, well, the size of the inputs, b, the number of neuron times 1. It will be all summed together, creating n, the output that will be passed to the transfer function. In this case, the transfer function is Hall-Limbs. So a, the output, will be given by the function Hall-Limbs inside w times p plus b. W is the weight matrix, right? So from this general to single case, this will be the two input case. We will receive two inputs, P1 and P2. And since we want to classify these in two classes, we only will have one neuron. Before we continue, like the text mentioned, with the orange and apple recognition problem, which we will require a three-input perceptron, because the these prototype vectors have three elements. In this one, we are going to give just two elements. It will be useful to investigate the capabilities of a two-input single neuron perceptron, which can be easily graphed and analyzed like this. Single neuron perceptrons can classify input vectors into two categories. That's the Hall output. For example, if for this two-input perceptron, if we declare, just imagine like this, the weight matrix as -1 and 1, then the A function will be like this. So the inner product will be depending on the p values, like the p vector we're adding here, -1, and let's understand why that's -1. Um, the output will be 1 if the inner product of the weight vector and the input is less than b. So for the moment, I want you to not take a look to this. You can read it later. Mufad Al Hakim says hi. Sorry, I see the comment. Hi. Um, but I want to introduce now a thing that's called the decision boundary. And the two input case, again, it's good to understand this because it will give us a graphical idea of how this looks. Even the three input case we can graph three dimensions, that's not a problem, but in two dimensions you can see this better. Imagine you have the two-dimension input P1 and P2 on the x and y axis, respectively, and then we have you will have your weight vector. Remember, in this case, it's a weight vector because we have two of value of r and one neuron. This gesture shows balloons. Um, Sorry, I got distracted. So r is 2 and s is 1. So this is why the weight matrix in this specific case it's a vector, right? So for the vector, that it's here, we will have a decision boundary, so we can draw a line that it's orthogonal to this the weight vector that will give us the classification. So this is our P1 and this is our P2. If we test with another P, let's say 1 and minus 1, it will be 1 here and minus 1 here. The point will be around this. So classification, as this mentioned, if n will be less than 0. So it tells us the classification will be 0. Let's do another example. If the test vector, let's say, for example, it's 1 dot minus 1 dot 1, like slightly here, and 0, I don't need to go up here. Just being on the gray area here, the classification will be 1 because we are in the gray area. So every point that appears in the gray area, it will be classified as 1. The rest will be classified as 0, right? So this decision boundary help us to graphically understand what we are doing here, more in the case of 2 inputs and 3 inputs. If we take it to more dimensions, it's harder to understand graphically, but once we create this mental model to help us understand how decision boundary affects the classification, like basically not affects, like it is the one who's taking decision on how this will be classified. You know, uh, the key point here, it's that decision boundary, for example, because we propose the weight function as minus 1 and 1, so meaning I need to go minus 1 and 1 here. I told you that the decision boundary is orthogonal to this vector, but I didn't tell you where it's going to be put at. It's going to be based on this function. So decision boundary will exist when this criteria is met, where W times P plus B it's equal to 0. If we already created W and we have it here, we just need to propose a vector or something that give us the B we want. In this case, we can decide, for example, 0 and 1. So the point here, it is going to tell us that the decision boundary is going to cross P2 on the 1 value and and no movement on 0, or it could be minus 1 0. That tells exactly the opposite. It's going to cross P1 in minus 1, and it's not going to cross P2 in 0, right? So that's how we design this decision boundary. And we will check. It's nice to be back here. Shelstronic, hey, thanks for joining again. So, if we take this to the third dimension, the decision boundary is not going to be a line, but it's going to be a plane in the three-dimensional space, separating the the sorry the area. And at this point, now that you can understand this in a more graphic way, I want to notice. I want you to notice something that you probably didn't think of before. Even for Hamming network and this perception, classification can only be made with linear separable problems. So what does that mean? And I will show you a graphic that represents that better. But it means that, for example, if I have a point here, and then another point here, and then another point here, that cannot be separated using just a straight line, but it will need function, I don't know, like a tangent or some sinus or something like that to be separated, then these algorithms cannot classify that. They need to be linear separable functions with linear functions, of course. So, in a graphic way, you can understand that much better with this decision boundary, right? So now let's take a look to that pattern recognition using the orange and stuff, and well, the fruit example. Because there are only two categories, we can use a single neural network. Because the rule for the number of neurons in perception, it's going to be S, meaning the number of neurons, elevated to 2, that being the number of classes we can classify. You know, if you want two classes, you will have just one neuron, one elevated to 2. If you want four classes, you will have two neurons, two elevated to 2, and so on and so on and so on. So in this case, we only want to classify two things: oranges and apples. And both prototypes have three elements in their values. Um, let me recall. It was shape, texture, and weight. Yeah, exactly. So the A output will be looking like this: hard limbs containing the weight matrix. In this case, since we only have one neuron, it's going to be a weight vector. Uh, Remember, a vector, it's just a specific case of matrix that will be multiplying for these input column, right? Plus the bias. We can choose the bias and the elements of the weight matrix so that the perception will be able to distinguish between the apples and oranges. So in this case, we are defining and we are setting, like, fine tuning the weight and the bias to consider the classification of the orange and the apple. So that's why here on the graphic we have these vectors, the orange vector and the apple vector. If we inspect it, we can see that the plane that divides these symmetrically, it's the plane of P3 and P1. I want you to remember what I mentioned before. There's only one value of the weights and the bias that can apply and can separate these problems correctly. Actually, since we have a very limit prototypes and very limit examples, there are infinite solutions to this, because there's an infinite number of planes between these orange and apple. Not all of them, actually, just this one. It's going to separate them like in a symmetric way. So that's why we are choosing this one. But many other planes, many other decision boundaries are going to separate them and classify correctly these two prototypes. So once we notice this P3 and P1 plane, it's the one that separates this, we are going to choose it. And then the equation for that, it's going to be P2 equals 0. So the output, the weight matrix will be 0, 1, 0, right? Now we need to find the bias. And for that, remember, uh, we need to, in this case, we need to equal all of these to zero. So therefore, bias it's also zero. I hope that makes sense. We doesn't need to move the plane any other. In here, for example, we needed to move the bias, sorry, the plane, a little bit to the left and a little bit up. That's why bias was -1 here, right? So same as in other mathematical functions, when you add to the graphic, you move in an axis the line. Here we don't need to move the plane in any direction. Actually, it exactly there it's fine. So that's why bias is zero. Again, the weight matrix it's orthogonal to the decision boundary, and it points to the word that region. Sorry, towards um, to the region that contains the prototype pattern. In this case, P2 it's the apple for which want perception to produce a positive output. In this case, it's how we design it. So it doesn't matter actually if we want in this case, for example, if this is the plane, this will be like the weight matrix pointing towards the apple vector. Um, but it doesn't matter actually. It's just by us designing. If we want to do it the opposite side, like the weight matrix pointing to the orange vector, then classification of orange will be +1 and the apple will be -1. In this case, it's the opposite. We designed it to be apple positive and orange negative, but it's how we interpret the output data. So it's the less, unless you have a specific requirement in which this come handy to know. So, one with that in mind, let's test the or design or values of the weight and the bias using the prototype vectors. Remember, we use the prototype vectors here in the graphic to decide it and to check this works, but it's not like in the Hamming one. Here we're not feeding the network with the prototypes. We just design it to get the values of the weight and the bias, but the network itself doesn't know the prototype vectors. So it's a good thing to test with these prototype vectors to see what the output is. So for example, orange give us the orange, apple vector give us apple. And this is what I was talking about. Orange give us a -1 and apple give us a 1. If we're using Harlem and not Harlems, this will be a 0 and this will be a 1. Binary output. And that's it. That's all we needed. So now let's test another value, one that's not from prototypes. And this, for example, -1, -1, -1 point will be -1, -1, and -1. This is P1. This is the one we are testing. Don't confuse the prototype vector P1 orange with this P1 test. I know it can be a little bit confusing, but at least they help us with the sorry, I was confusing even this. This P1 it's not the test vector. Sorry, this is the axis of the three-dimensional space. Well, it is not graphed here, but if we can add here another, let me pink -1 in P1 be like this. Oh, come on, I want to underline. No, well, I cannot draw. Uh, that's a shame. Sorry. But if you go -1 here in P1, -1 here in P2, and -1 here in P3, you will have your point around here, pointing from here. Have a three-dimensional space imagination here. So graphically, we can see that's in the side of the orange, right? I talked you about how we can take many planes that separates oranges and apples that are not symmetrical. So we could choose a decision boundary, for example, rotating this plane that separates P1 orange and P1 apple, but that contains this new test vector inside the apple size, you know? But this is not the case. That's why I mentioned we have very limited information and very limited data to decide which will be the decision boundary here. So for us, it works fine, the one that is declared. And based on that, based on the one we choose before, the classification of this new test point will be here, this this test vector. And that's exactly that. The classification give us -1 for the orange, right? So that's how we design the neural network of perception. Let's open my uh, notes and let's do some other examples by hand, and then we can pass to do them on code. Um, that will be very quickly. Give me a second to connect the drawing thing, the iPad, uh, and I have prepared some examples. Okay. Let me. Sorry, it's getting slow. Got freezed. I hope you do. Mm, okay, it's not detecting. Okay, yeah, I think it is now. Okay, it has a little bit of lag. Okay, but should work here. And let me make this bigger. So, as I was mentioning, there are some examples here we can try to reproduce to make this better understanding. So, in the end of the chapter, we have this exercise. So, In this chapter, we have designed three different neural networks to distinguish between apples and oranges, and based on these three senses measurements, shape, text, and weight. Suppose that we have distinguished between bananas and pineapples. So this is very simple, and this is a very simple example because we just need to change the prototype vectors here. So let's design a perception to recognize this pattern. The first thing will be do the same, like in a graphic way, draw these to see how they behave. Okay, I think I messed up with that. This should be here. Yeah. So same, this will be P1. Sorry, this is P2. This it's P1, and this is P3, right? Um, so let's find those points. We have bananas and pineapple. Let me pineapple, yeah, minus one, one, and minus one, and this will be minus one, minus one, one. Nice. So minus one here, minus one in two, and minus one in three. So this will be around here. Pineapple will be minus one in two, and one in three. So let's imagine this is the one. And well, for me, I think that the best option will be use this same uh, vector, like creating a plane in P1 that it's rotated 45 degrees here, you know? So that could be an option. That could be just one possible solution. And for that, we need to define a weight matrix that is orthogonal to that plane. Remember, the direction of the plane, the direction of the weight matrix points to the vector we want to classify as positive here. So in this case, we can add this weight vector pointing here, and that's meaning the oh, I didn't. This one was banana, and this was pineapple. So banana will be classified as the positive one, and pineapple will be classified as the negative one. You know, that's simple. Um, Let me take a look to this one moment. I want just to make sure of something because I have this prepared in a better way. Okay, yeah. So I copied my exercise and I'm pasting it here because now I sketch it quickly. But here's the same, like the same but better explained. Um, this it's defined as, again, as a Harlems. We want to create, or we want to define uh, the values of the weights. Since again it's in the center and it goes through the center, 0 0, without having the necessity to move this plane in any direction. The bias is still 0, which is this. The bias is still 0, and the weight matrix, it's the plane of P2, and it goes on the direction uh, 1 and -1, and 0 here. So no movement on P1, 1 in P2, and -1 in P3. That's the orthogonal movement we wanted. So based on that, we have these values, and this is our final function. Now let's test it. If we test it for the pineapple, we need to substitute this data. Um, Again, I have them around here. Let me go to a different page. Let's open a new page here so we can understand this better. Oh, well, no, it's not necessary. It fits well here. Yeah, nice. No, no problem. We tested with banana values, so same values here. We have the same weight matrix, same bias. Now we just substitute with the vector of the banana, -1, 1, and -1, right? So if we perform this calculus, this will give us Harlems 2, meaning it will be classified as 1. So remember, this is the banana vector. It's pointing the same direction as the weight vector. That's good. That's what we want. Let's do it with the pineapple. We substitute -1, -1, and 1, which is the one we have here. Same weight vector, same matrix, and we have a -2 passed to the harm limbs. That's mean -1, so it's all classified. Finally, let's try with a new vector, that one that it's not in the P3 or P2, sorry, in the banana or in the pineapple prototype. And we said 1 in P1, -1 in P2, and 1 in P3. It will be something like this. Uh, so we know it will be classified as pineapple. It will be a -1, so this is same as pineapple. That's all the proofs we wanted to know this is well designed. Nice. So for this exercise, we complete the classification, and it's the same that it was on the book, but changing the values. That's exactly what we wanted, right? So let's try to do another one that it's a little bit more complicated, and then we move to the code, and then we move to the learning rules, not making or not designing or not calculating the weight in a graphic way, or the bias in a graphic way, but making the algorithm to calculate it itself. Consider the following patterns. Find decision boundary. For the precision line, we'll recognize these two vectors. Okay, this is an interesting one because it's for defining the decision boundary, but we want to design a perception network. Okay, yeah, better this. We want to design a decision, a perceptron network to output a 1 when either of these two vectors are input to the network, and a -1 when either the following vectors are input to the network, right? So it's very similar to what we've done right now, but in two dimensions. So it can be a little bit simpler, but it can help. It can help us a lot to understand. Um, let's open a new page, but let's check the results from what I had here. That's 3, 5. Okay, now, nice. So let's check the discussion here. Um, we have these values for what we wanted for 1, and these others for a -1, right? So these are ones and these are -1s. If we draw them in the graph, uh, these are the blue circles, right? -1, 0, and 1, 2. Sorry, the green crosses. So these ones are the green crosses, and these ones are the blue circles. That meaning, what one thing that we're missing here is the weight vector that should be pointing this direction, right? Because we want to classify. Oh no, sorry, I do it wrong. Actually, weight vector should be pointing here because it's pointing towards the direction we want to classify as 1, and this will be classified as -1. So we propose a weight vector that is this one, 1, 2, and 2 in -2. Um, actually, this one's not correct. This one should be like this. Yeah, uh, 2 and -2, right? So this pointing this direction. Nice. The bias should be the rule of the bias should be W times P plus B equals 0. So bias here, it's meeting this criteria with this point with this vector matrix we proposed, and we just need to select a point, in this case, for example, 0 and 1.5, because the decision boundary crosses that line, and bias will be -3. So in this case, it has a value because we need to move them from the origin. Otherwise, decision boundary will be here in the center. So we move it here at and the value it's -3, right? Hope it makes sense. So this is how the network looks, and these are the values that we're using. In this point, we already have weight and bias values. so we can start uh, checking the solutions. And if we test the vectors they gave us, like with the weights and bias we set, we check it classifies correctly the outputs. So at this point, you already understand it, what perceptron is, how it works, how we can design decision boundaries to classify linear problems, linear separatable problems, and how we use that in order to make classifications. For vectors of n size that it's easy to graph, just 2 and 3, it's very simple. But now imagine that we have a vector of uh, 5 dimension, 6, 7, 9, and etc. It cannot be a simple solution to just graph it, draw a line, draw a plane, and get the weight and the bias values, is it? Well, let's go to the next part where we are going to define the learning rule for the perception. So we need to move here to the next chapter, and we are going to remember the perception architecture, right? Um, some things I haven't mentioned, I think we don't. If you want to explore more about these perception, you can read more in depthly this chapter. But I think I'll already cover all what it needs to be covered. Um, More graphic scenarios, for example, how these are classified, the decision boundary orthogonal to the weight vector. Here, these ones are going to be negative, this one's going to be positive. Um, okay, I think it's worth taking a look to the multiple neural perception area because it's the one I mentioned. Um, Sorry, I think I mentioned this in the opposite. I didn't say it 2 elevated to s. I said s elevated to 2. My bad. I correct myself here. So this is the output vector can be either 1 or the total possible categories are given by 2 elevated to s, where s is the number of neurons, right? So, yeah, that's another consideration. Perception learning rule. And I think what we need to explain here, it's very similar to what you need to do in your mental process to try to resolve it. And it's very, very nice, this picture, because yeah, it gives us the better idea of this. Imagine you have this problem, these 1, 2, 3 um vectors, and you want to classify just the first as positive and these ones as negative. So you can start with a decision boundary that's pointing any direction, whichever direction you want, and then test the output of that and see what the results are and what you're missing. And based on that decision, you will have an error. And depending on the error, you will start moving your decision boundary to see if the next time you move it, you reduce the error or you increase it, you know, and then keep moving that decision boundary each time. This is where we introduce concepts like epochs, we introduce concepts like accuracy and error. So the problem is displayed graphically in the adjust figures, where two input vectors whose target are zero represent with a blank circle, and the dark circle it's with for one. This is a very simple problem. But for constructing this learning rule, we will have to have these things in mind. I'm going to skip all of this. And yeah, the things that we will have in mind is that if t, meaning t, um, you will see. Uh, sorry, I think I skipped it wrong. Uh, where it was another possible blah blah blah. A zero. Yeah, t it's for target. Sorry, I forgot that. Um, so I need to introduce another concept here. Sorry if I skipped that. This learning rule for the perceptron it's going to be under the criteria of supervised learning. What does that mean? Supervised learning it's the type of machine learning that it's based on values and targets. So you will say these values should have these results. In this case, we're going to call it a target. So the vector 1 comma 2 should be target 1. The vector minus 1 comma 2 it should be targeting 0. Vector 0 comma minus 0 dot 5 should be 0. So now if target it's 1 and we wanted, sorry, if the target is 1 and the output is 0, that means we're wrong, then we adjust the new weight matrix doing the old weight matrix, and we add the the vector, the one we use as the input, and we explain it here. um, it's around here. Yeah, so it's in the images. So you start with your weight matrix pointing any direction, and you checked that you missed. So if you missed in the the classification point you're looking for, it's in the middle of that. You add it. So the next time it will be a vector in the middle of those two. So it's a very good way to do this. And the next time you keep adding the the addition of the vector to that. So it will move the decision boundary towards the direction you're looking for. A more detailed explanation of this, again, can be found here. For the moment, just believe me. Trust me. uh, Again, if the target is 0 and A it's 1, then you miss it again. So instead of adding the vector that you entered, you need to subtract it. So you move the decision boundary in the opposite direction. If it's the same, like if the target meets the classification, then your weight matrix it's good. To make a unified learning rule for this, we introduce the perception error criteria, which is the target minus the classification. We can now rewrite these equations of before to see if the error is positive, if the error is negative, or if the error is zero. It means no error. and it will be almost the same. If the error is positive, we still need to move uh, the decision boundary towards the direction that we were looking for. If we hit the the error as negative, that could be meaning, if we part from the idea we were moving this direction, that we need to return because we passed the point we wanted. And if you imagine this as I am doing it, it can sounds very similar to control systems like a PID, right? Uh, so yeah, it could be very similar in concept, that we need to uh, make oscillations over a line until we hit the desired one. You know, um, so we can have different functions that can help us to get it sooner, to not bounce between values many times, and things like that. That helps in theory, in control theory. But finally, we wrap up these three different rules in just one simple expression. The new or the latest weight matrix, that's the one we're looking for, it will be equal to the old one plus the error times the vector, or error, remember, it's target minus the classification return. And same for the bias. I mean, we have to remember, bias is another thing we want to get. But in this case, we don't add the or multiply the error times the vector. So that's it. For training multiple neurons perception, that will mean that the weight matrix, it will be different for each neuron. So remember that the weight values in the weight matrix are different for each different neuron. Right? Amazing. Um, yes, no. I want to make a clarification there. The weight matrix, if we remember this, it's going to be all S. In this case, this is just one neuron. But if we make two neurons, for example, 2 times 2, this all weight matrix, it's going to be the same in this representation. What I want to say it's different, it's that we are going to do row by row of these matrices, of these vector, how to say it, yeah, vector networks, sorry, vector of the weights. So that's why this is working. And same for the bias, like each row in the bias, in the final bias column, it's going to be a new thing to learn for the algorithm. So that's why these rules have this one, one, and one. It's because it's the first row. Well, sorry, it's in this case it's a one, but yeah, it should be like this. It should be an I, because it's going to be depending on the row that they are in the neuron that they are. So just have that in mind. Well, more mathematical proof of that, the concepts. But I think we're ready to finally hit the MATLAB. And um, this, for example, the problem illustrated graphically of the limitations, and this is very important section. These ones are problems that we cannot resolve, because imagine, draw a line that can classify this. You can't. They are not linear separable problems. Same like this. You cannot draw a simple line here. You have to draw like uh, very specific function that separate this, um, and we have not the criteria for that. Even an XOR logic gate, that's the first element here. This is not possible with perceptron, and that's very interesting. Uh, but yeah, let's open now MATLAB. Okay, MATLAB doesn't want to be open now. Come on. What's happening? Come on, MATLAB. Don't be shy. Get out. I was thinking late to the party. Is this book unlocked by chance? Yeah, I shared the link in the part one. It's completely free, but also there's a physical book that you can buy, and I do recommend that. I think that's a really nice investment. But let me look for the link while MATLAB decides to open. I don't know what happened. Okay, here's the link for the book. Oh my god, what's happening? I'm going to close this. Reverse changes because I didn't want to make any changes at first. Come on, MATLAB. I'm going to close it completely. Like, quit. Yeah, don't know what happened. Sorry for the difficulties. Give me a second. Now I'll try to open it again. Much appreciated. Don't worry. Okay, should be closed now. And I'm going to close other things that I'm not currently using. That may be a reason. Come on, MATLAB. Okay, now it's opening. Nice. And very similar to what we did on the Hamming network, I want to show you that I built this to be object oriented, like I create a class definition. So every time we use it on the implement file, we just need to call the class and create an instance of it. In this case, we're going to implement the perception network, but with learning. That meaning we are not going to pass the weight and the bias as the previous as the Hamming network. In this case, we're just going to pass the training prototypes. The properties are defined as the weight, the bias, and the transfer function. On the constructor, we just set the weights to be a random number of the input size, the bias, a random number of the number of neurons, and the input size. Remember, that's the definition of the weights. The bias, it's number of neurons, and one. The transfer function should always be Harlim. In this case, could be Harlims, but let's stick to Harlim. The output of classification, they will be exactly the A we talked. A, it's equal to W times P plus bias. That's it. That's all. And that's the N. N passed to the transfer function, which is Halim, and that's all. That's A. Nice. Let's take a look to train, which is more interesting. We received prototypes, epochs, and we return the object, and we return stop code object because we updated weights and everything, so we'll need to update the class. Stop code because we need to know if the training was stopped due to all criteria met, like all classifications were correct and we're ready, or because we run out of epochs because we set a max epochs, right? Um, so we start initializing epochs to zero, and while not all predictions of the prototypes are correct, that means we are going to train this until all predictions are correct, or we hit the max number of epochs, right? So every time we increase the epochs in one, but for every element in the prototype, we get the input vector and the target vector. Um, I'm going to show you how that looks like. For example, we can have an input vector of 1, 1 and a target vector of 1, 1, 2. Why target it's 1, 1? Well, because for this example, we want to classify 4 elements. We didn't see that on the book. I think it's an example, but we didn't see that. We didn't check it. I want to show you here in the code example how will that look like. But yeah, it's a vector because it receives the classification of the first neuron and the second neuron, right? Remember, for 4 classifications, we need 2 neurons, right? Amazing. Um, so yeah, the input and the target. We receive the prototypes. The first element in the whatever prototype we are looking, it is the input, and the second element in whatever prototype we're looking, it's the target. Nice. So for these two, we classify. We use the classify function we created, well, method we created before. Now, remember the learning rule. Here we could do 2 things. The first one is to check the 3 values to decisions if this classification it's 1 and the target was 0, blah blah blah. If the target is 1 and the classification is 0, do another stuff. But remember, all of them was resumed in this nice expression. Every time the weight it's going to be updated as the previous weights plus the error, which is target minus classification, times the input vector. And bias, this is going to be updated too. So that's it. That's so simple, right? And we do this for every element in the prototype. That's an epoch. And since we we can do this more than 1, 2, 3 times, 100 epochs, let's say, we just need to check if the classifications are correct. Normally, for these examples, we don't need that much epochs because if we take much epochs, it's because we are doing something wrong, probably. Uh, but these are again very limited in the amount of data we have. Here, we are only training with 4 prototype vectors, so not much problem for that. Then we log the progress. Um, we have an accuracy. The accuracy method that we called, it's defined here. So we just calculate the accuracy of the perceptron on the provide prototypes. Again, we checked and we run the classification for every element in the prototypes, and we checked if the target and the classifications are equal. Like if this is classifying right. If so, we return the accuracy as a fraction of the number of uh, counters or the number of elements we have. But yes, this is just for logging. This is just for like the developer experience, you know. Um, then we graph the results. Finally, we make a plot of the results. I'm going to show you this method. And at the end, again, we need to see if this training was stopped due to which one of these conditions. Because epochs max epochs were hidden, or because all classification is correct. If it's because of the epochs, we set this top code to 1 and to -1, and we can try it again. We can try it again. We can try it again. You know, we can do interesting stuff there. If no, if that's why, if this is due to successfully training, we set that, and that's all. The correct one, this method that we are checking here for the prototypes, what what this does, it's that it check all if all the classifications are correct, and very similar. Again, we checked and iterate over this, um, and yeah, that's it for the plotting. Well, this it's a really big method, but it is because I tried to be very detailed. We initialize the figure, we add the x and y axis. For these specific scenarios, we're just setting limits to 2 and 2, so no big numbers here. A little bit more for make it more sweet to the eye, I will say. The labels, define the colors because I want to differentiate in a color way all the classes. I also checked if the prototype length. Oh, another consideration here, another boundary, it's that these work for only two-dimension inputs and for 2 and 4 classes to classify. Else, this can predict. I mean, all the training and all the other things works, but the plotting, the graphics won't work. That's a thing to have in mind if you want to do if you want to check the code of this in the repo I shared, and well, it's yours too. But yeah, it won't work for more than two size inputs. I mean, 3 dimension won't be showing the plot, and more than 4 classes, no, it will be a no go. But yeah, it's just not neural networks, but it's just data visualization. So I think it enters in the scope of the session, right? So let me explain. Uh, yeah, once I initialize, set the boundaries, the colors, blah blah blah, I will iterate over the prototypes again to extract the points. If the number of classes again it's 2, I will do this. It's equal to the target to set the class index, and then once I have the class index, I will be to the lower point. I scatter that class index to the color to set red, green, magenta, or yellow. It depends if this is for class 1, class 2, class 3, or class 4. And then I calculate the coordinates for the decision boundary lines. How we can calculate this? Um, well, we were doing the opposite when we were designing this in the graphic way. I mean, we set the line we wanted, and then we calculate weight and bias, right? So now we need to do the opposite. Now we have the weight and bias, and we need to calculate the the line, the graphic, the math equation for the line. So first I set the boundaries for all the line space we have. Then the equation of the line will be given by minus the weight of the first value of the weights divided of the second value of the weights times all the boundary minus the bias divided by the second value of the weights. This equation, you can have it from the same W P plus B equals 0. That's where I get this from. Plot decision boundary line and draw the weight vector as an arrow. Um, and this is just to show the weight vector that's orthogonal to these ones, right? And well, for if the class is 4, we do the same, but we add an extra. Actually, I need to remove this. Okay, I will do it later. Don't worry. We add an extra line. We add an extra plot. We add an extra arrow here. So that's it. Let's start checking implementation. So for this specific example, we want to draw 4 points in this line. And take a look to how, remember weights and bias here starts randomly. So if we see this, and I told you as humans, I want to classify these 4 elements in the spectrum different, you could say, okay, one decision boundary could be x axis, and another decision boundary could be y axis. So why your program it's doing all of this? Well, it's a solution. Again, it's a valid solution because I'm just telling the program to classify it using these 4 elements. And for these 4 elements, if I put them again, so if I test them, the solution will be exactly the same and exactly what I wanted. But if I run it again, let's wait until this is shown. Okay, yeah. If I run it again, it found another solution because again, weights and bias started randomly. And this is another solution, and this is same valid as the previous one, since we only have these 4 training prototypes. Now, based on this, I could start playing to classify different data. So this section here will be classified as 1 1. This section here is going to be classified as 1 0. This here is going to be 0 0, and this is going to be 0 1. So let's test it. A point in -1 1.5 should be classified as 0 1, isn't it? So let's test it. Test perceptron dot classify a point in -1 1.5. And this is classified as 1 1. I did something wrong? -1. Okay. Let me check that I'm doing this correctly. I mentioned minus 1 1, it's 0 1, minus 1 1.5. Yeah, this should be actually, this is wrong. Wait, why is that? I'm looking the correct decision boundaries. I think I am. Positive, positive. So yeah, this is 1 1. Positive, negative. This is 1 0. Negative, negative. This is 0 0. Uh, Positive, negative. This is 0 1. Yeah, this should be 0 1. Um, okay, let me let me look. Why could this not be working? 1 1. Wow, interesting. Can you graph the new point? Um, yeah. The thing is that I ended the hold up here inside this one, so I don't think I could. Uh, but but since this was already closed, one thing I can do is try to replicate this value minus 1 1 instead of 1.5 to see if this classification is correct. Yeah, it's 0 1. So let's start increasing this to see where it breaks. 1.4. Why then 1.5 breaks? Wow, 1.5 minus 1. Am I talking about minus 1 here and 1.5 here? No, no, I mean that's not correct. Wow, very interesting. Didn't realize this was failing because I tested with the prototype vectors. It's because the slope is so close to the right point. No, but the point should be around here over the magenta because this is minus one. Oh, am I doing minus here too? No, no, this is positive. Okay, because for example, minus 1, 0.5 should be 0, 0, minus 1, 0.5 of positive. Yeah, so this is wrong too because this is here in this point, minus 1, 0.5 here, sorry, minus 1, 0. Okay, yeah, this is correct. 0, 0. You may be right about that. I may be doing something wrong with these where I'm drawing the lines. Let me check something. Uh-huh. Line. Initialize class 2, class 1. I'm multiplying weight 1, 2, 3, 4 to decision boundary. Yeah, bias. Okay, let's do something quick and remove this bias. And remove this bias. Okay, let's try it again. Come on, load. Okay, here. So let's run this again. Okay, so as you see, there are different biases here. Uh, for example, this line, it's exactly on 0. So if I do 1, 0.1, or 0.1, 0.5, positive, and 0.1 positive, I should see 1, 1, 1, 0. Okay, that's interesting. 1, 0, it's here. Okay, maybe the line it's not crossing entirely here. Let me increase this by 3. 1, 1, yeah, exactly. Okay, so this line and these lines supposed, well, at least this line. Let's now test this with 0.1. Yeah, minus 0.1. This should be then 0, 1, and still 1, 1. Okay. So this line is not, and but this is another line. Let's try to minus 1.1. Well, minus 1, not necessarily the dot 1. 0, 1. Okay. 0, 1 minus 0.9. 1, 1. Yeah. So, okay, I think I know what's happening. Let me look for bias in other parts. Wait, it's updated. Bias, it's updated. F, bias, bias. Bias, object net input bias. Yeah, I was displaying the wrong uh, bias. Well, I was using the wrong bias to display this. So in this case, I was using the 2, and I was using 1 again. So let's try it this way. Glad you understand. I'm a little bit lost. I'm sorry. Yeah, so it's the thing I was mentioning about. having different weights and bias for each neuron. That was kind of a lie. I mentioned it, and I showed the diagram, because it's not that you have different weight or different biases, but each row in the bias column represents the value for a different neuron. So for the first neuron, uh, I mean here the first neuron, the first element of the classification, you have a bias value, and now a yeah about bias scalar, because bias, it's going to be a column vector, and the weight matrix in this case, it's going to be 2 2. The first row, the first vector, it's going to be for the first neuron. So um, I was showing or doing the calculus for the decision boundary with the incorrect value of the bias. That was happening. So in this time, I used both values of the biases to display the lines to see which value was the correct. I hope that helps better. So in this case, this line, it's not the one I wanted, and this line, it's not the one I wanted. So this and this were the lines I wanted. But that also means something, that probably this will be misclassifying the red. So at some point, not only in the decision here, or sorry, in the showing the graph, I'm doing something wrong, but also I am doing something wrong in the calculus. I hope I'm doing something wrong only in the graphs, because displaying wrong a line, it's okay, I can fix it, but in the calculus it can be a little bit more complex. So um, I hope I give you a better explanation of what was happening here, of what I think what was the error. Yeah, for example, here, this works fine. But let's test it. Okay, I'm going to run this again, because I want another boundaries that are easier to. Okay, this is easier. 0.5, for example, that will be here, and a little bit up 0.5. This should be 1, 1, 1. Nice. And in 0, this should be 1, 0. Nice. And minus 0.1, this should be 0, 0. Nice. And in the same, but if I dot 5 here and I go up, this will be 0, 1. Perfect. Thank Thankfully, I was in the right thing. I was just messing up with the lines I was drawing, because I was performing the calculus of the uh, the line with the wrong bias, but just like that. Um, yeah, thanks for the heads up there. What next? What else? Well, here, for example, I have a test input representing some other values, and test targets representing some more values. So these are files, and this next section, it's going to read these files and show us the result for that. And this time we are going to classify just two. So first we need to select test, and then we need to select the targets. Nice. So these are the points. We see that all in the left of the line, it's well classified as one, and all to the right, it's classified as zero. So we checked the weights and the bias here, but we forgot to check them here. See how weights here are a matrix and bias it's a column, and here it's a vector, and it tells color. This is the one thing I was mentioning, skull crusher for life. This first row corresponds to one of these lines, and this first row corresponds to the same, and this second to the other line, and this second to the other. So we can check this 1.792. This it's the black vector for the matrix, minus 0.34. It should be this one. So yeah, we are for sure. This is the one we're taking a look. So the next one, it's minus 0.04. So this is minus 0.404 and 1.035. So this it's the second weight matrix, right? Not only the colors tell you that, but the values tell you that. Same as the bias, both are a little bit separated from the origin. So in this example, it's not distinguishable. But here, for example, the bias it's 0 to 74. So it's the separation here. Actually, it's more desperation like here, but it doesn't matter. And the weight matrix, it's pointing towards this direction, minus 3.3 and 0.75. So that's it. Remember, the important thing about these designs are the weight and the bias. Weight and bias, it's like the soul of your neural network. Without these values, I mean, if I change these values of weight and then change these values of bias, then decision boundary will be in any other place, and classification will be doing wrong, similar to what was happening here. And for the question Malik asked me, in I think was the first or the second part, like, can we do this for real world applications? I will tell you yes, of course. And even though doing the process of calculating the correct weights and bias can be done in a local computer, having it, for example, here on MATLAB or anything that helps you perform, and with that values, you can take it to Python, to JavaScript, to whatever other function that now just have the network definition. And with the network definition, with the architecture, and with all of that, with the correct values of weights and bias, you can do a lot of things. So this imagine it's a fruit classifier. This imagine it's more than that. It's all the classifications you can know. So, uh, since we are really close to ending the session, I would like to ask you, do you have any question or anything I can help with? I hope this session helped you understand the perception network. Perception network, like the architecture, it's really simple. It's just one layer of n number, well, s number of neurons that you can use to classify, depends on the number of classes you want. And the important thing here we saw, well, the most important thing we saw was the learning rule, how we can act and build ourselves or neural networks. If you had done artificial intelligence before, you probably used the libraries as PyTorch, as TensorFlow. Well, inside they look like this. So I hope this session also will help you understand more like the inner part of what you probably are already doing. Um Take a look to part one, to more theoretical explanations like this, and take a look to part two to check the other network without doing learning stuff. So without doing artificial intelligence, just pure neural networks, right? When do you add more data to your training set? Where you were training off 4 points to test a fifth, when you decide to add more training data without overrating. Okay, I'm trying to understand when do you decide to add more training data? When you were training out for points to test the fifth. Okay, yeah, I think I get you now. Let me start presenting again. For example, for this one, I just had these 4 training points because this is the only thing I cared about for classifying. Imagine that you are sure you will have just these 4 prototype vectors, and you will have to classify it every time. Um, yeah, perception will be an overkill for that, definitely. But that's the only way you can assure the output is going to be all time correct. Else, if you test it like me here, for example, with this fifth value, and let's say you want now a value here on the this point to be also 1 1. How these weights and bias are right now, this is not going to be 1 1, this is going to be 1 0. So then you have a problem, and then you have to train it again with that new test data, you know? And for doing that, you can start from 0, yeah, of course, train it again. But also, you can do another thing that it's not here on this example, and it's not coded yet. But you can set the weights and bias that you had from previous. I mean, if I test it again, uh, oh well, no, actually, it's defined. Yeah, sorry, I was thinking wrong. If I test perception dot train again with a new prototype, if I add these new prototypes, weights and bias here from this test network are the ones here. So it will depart not from random numbers again, but it will depart from these previous ones they have, and it will fit now the new model. So you don't overtrain it because that's what you wanted. Now, in this case, you're telling me that, well, in the example, of course, you're telling me that the value here that you want, this value that you want, needs to be 1 1. But in the case you have the questions, like, I have the values, I don't know what it should be. Perception. You tell me, then you trust your network and see if it applies correctly. You know, like for example, um, for number or digit recognition, it's like very simple. Um, a one is a one, a two is a two, a three is a three, and etc. But with much complex problems, uh, when even you don't have like the idea of if the prediction is correct or not, then you have to trust your model. And with more and more data, then you will have more accuracy of that what you're doing it's correct. Like for example here, if I only give these 4 points, they are symmetrically separated over the axis. I could just simply say that this could be wrong if I choose a point around here and it's not 1 1. But what if it is not? What if it is correct? You know. Yeah, so you understand the question. Sounds like when you have better data, when you know that the fifth point is the ground section, you need to retrain the model. Yeah, exactly. When you know the the correct output, I will tell you that goes into the training. When you don't know, like you just want to classify it, you trust your training, and that will be the answer for that. So, yes. Well, uh, very good questions here. Thanks a lot for joining me. And that will be it for this session. On the next session on Wednesday, we will be exploring another tools for MATLAB and another network which is Adeline. And Adeline it's a very interesting network because this far we have only seen classification, but Adeline also can classify and predict data, and that will be a very interesting use case. So see you on Wednesday. Thanks a bunch for walking me through this. Yeah, don't worry, it's Skull Crusher for life. And thanks a lot for all the other people that joined this session. I will see you around. And remember, happy hacking.